Oops. So this one, we are given systems. I think this is number 5. And the mass equal to 5, and damping ratio C is a parameters, and spring constant equal to 10. And then substitute sine, harmonic sine function, and with a certain magnitude F0. And so here in this formulation, we have 2 parameters here, okay? And here we want to determine the maximum value of the magnification factors. So, and again, here using this example, in our textbook, they also say this is the magnification factors, or it's saying amplification factors, or the amplitude ratios. And I think this term is the most commonly used in other textbooks. Okay, so I would say probably I just simply using this term to communicate with you in all the homeworks and even tests or our lectures. Okay, using this term. So basically, that one is to access to simplify, to exercise these equations. Okay, so let me rewrite this equation here. So here we already know, so let me pick up that equation. The maximum value equal to 2 zeta and 1 minus 2 zeta squared. Okay, we start from here. And for this case, if we choose the value of C such that damping ratio equal to 0.1, then this value is very straightforward. Then this value have a maximum, simply you plug into here. That'll be very straightforward, right? And that is I think the problem statement is like this. So we simply plug in the Z equal 0.1 to there, and that will be equal to 5.025. Okay, and for case 2, again, another exercise, say if we choose C such that the damping ratio equal to 0.3, then this maximum will be equal to 1.747. I think this exercise is very, very straightforward. Again, that is the fundamental. Just get a little bit familiar with this kind of the equations here. Okay. And again, when you do the calculations, and you better to bear this kind of curve in mind, and in a way you know which case, which region approximately you're working with, and you get some feeling about the system dynamics, the response. Basically, this page is a summary of what we about the curve. Okay, so here in this page, I put the equations here, and that is a phase angle, and this one, this phase angle is for the system substitute the harmonic cosine. One more, a little bit more complicated system is like this, and this one again is to exercise the first step, finding the equation of motions, right? And then from there we begin to start from whatever the information we have. So for this case, the information is this. This one is a single degree of freedom vibrations, and this last block, okay. and that is have the spring and damping, and this is the degree of freedom we choose to describe that is associated with this mass block. And also we have additional externally excited loading applied to here, and that is inside. And also this mass block connecting to a pulley, and this pulley pin here. And with this wire, we're assuming this wire has no flexibility, no elasticity, is a rigid wire, and simply to transmit force and displacement. And this pulley somehow connect to the spring and in this way. And this pulley has the certain moment of inertia. So I think this example is very typical for very practical problems. So for this case, we let us formulate the equation of motion first, and then we see what we are looking for. So the equation of motion. And the first one, we take the free body diagram on the mass. Okay, and this is the degree of freedoms here. Assuming we have the mass to displace in accordance to the direction we take here. So assuming the mass block we're going down by x. In such an assumption, we know the spring has been compressed, so that we have the spring force pushing up according to our assumed displacement, and this one is K1 x. And similarly, we have the damping force C times x dot. That'd be right? So that's C. Let me take C, okay? And then this is the force that applied externally. Let me just denote it as a f of t. And anything else? Yeah, we take the free body diagram. So we cut the wire here. So through wire, I say that the wire is rigid. Rigid, that means only be responsible for force and displacement transmissions. But the wire itself won't give us more trouble, more deformation, more force. So that means taking the free body diagram, I'm assuming this is the tensions, the internal force being transmitted in the wire is T here. Okay, and then through this wire, let me take another free body diagram on the pulley itself. So this is a pulley. So we're connecting to the wire. So here is a wire, okay, and then we take the free body diagram to the same wire. We cut at the same locations. So this tension, this force to here is an action-reaction, right? So that means that tension should be going down, because here I assume up, they must going down because of the action-reaction concept, right? Okay, and that is the first one. And then on the other side, because initially we assume the direction of the mass is going down. So the pulley, to provide the mass going down, the pulley must be rotated clockwise to provide a consistent motion at the end here that going down, right? So here, using this case, we decide the pulley will be go in that direction, rotate by a certain amount. Be good? Okay. So under this case, then we can translate that information. So basically, this is a spring, because right now, how to translate that motions? Because here we have the mass block. We want to have the, if you look at here, this mass block going down by x, that means this is a pulley the pulley rotation, let's say that is theta. So that means 2r times theta must be equal to x. We keep that in mind. This is our compatibility equations here. The pulley must be rotated by that much to provide the displacement at the wire here. Okay, and also here this is a pulley. This is the radius r. So from here you can see at this moment, if the pulley do the rotation clockwise, at where the internal and the inner the disc here is rotating is by r theta, and r theta is the displacement that transmitted to stretch the spring at here. So here I think the number is k2. So k2 times r theta, that is the force and being produced, generated in the spring. So that is a k2 times r theta, right? Good? Good. So we have everything, then we try to convert. And so from here, basically this term equal to k2. I want to convert everything in terms of x. So r theta equal to x over 2 here. Because here we only have a 1 degree of freedom. Theta is related to x. So you choose one, and here I choose x. So we convert all the theta related into x, and through these relations. Be good? Okay. So we have everything, then we can begin. So now we're using for this Freebody diagram, the mx double dot equal to all the forces equal to mx double dot. So for this case, let me take the sign convention positive downward. So that means mx double dot will be equal to minus k1 x minus c x dot plus f t and minus t, right? I take this positive sign downwards because this sign convention I simply follow up with my assumed directions for degree of freedom. Okay, and so that means this is negative, 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 positive, like this. So let me rewrite here. So the mx double dot plus cx dot plus kx and plus t equal to f of t. Okay, so that's the first equation. The second equation, let us work on the pulley here. The pulley basically is, there's a rotation. So we take the moment about the point O, the pivot, this is a pivot O, okay? Equal to I-O theta double dot. That's a rotational inertia. It's contributed by the summation of all the moments. Okay. So here again, here the theta taking the clockwise as my sign conventions. Again, such a clockwise motion will be consistent with our x here. So I take that one as that's fine. So from here we can have I-O theta double dot equal to, so from here the moment is contributed by all kinds of all the components of the force. And here we have 1 and 2, right? Only 2 forces. So from T multiplied with 2R, and that is positive. And then this force from spring produce a negative spring, so minus K2 R theta times R. Okay, so let me convert it into x. Sorry, here I2 double dot equal to T. What is 2R? And 2R equal to oops. Anything?
Just a constant.
can do it. I won't screw up. I promise myself. So let me do this one again. QR and this one K2 and R theta equal to X over 2. So let me do this one here. Okay, and multiply R. So here in this way, from here to here, I simply convert into this one. And now I want to replace the T from this equation. So from here we can have T equal to IO theta double dot plus K2 X over 2 times R and divided by 2R. Okay, so that is this one. And we have to do one more thing. And here, theta is related to x. We simply do one more substitutions. So theta equal to x over 2r. So from here, basically this one will be equal to IO theta double dot. That means x double dot divided by 2r plus k2 times x over 2 and divided by 2r. Okay, good. So in this way, that would be equal to IO and 4r squared times x double dot plus k2 times x 4r. K, oops, since I forgot this term. So here, please edit up this one here. I forgot that one. So that means here we only have x over 4. Be good? Okay. So right now we have everything. You will simply plug in this one into here. Then we come up with the single equations of motions and in terms of x. So that means n x double dot and m plus IO 4r squared plus cx dot plus k 1 plus k2 over 4 and x equal to f of t. And here the f of t in particular, that is, let me plug in here, that is f now sine omega t. Good enough. So here that is, yeah, I think that's the very practical applications. So basically this one compared to our standard form, if you remember, when we derive our equation of motions, the whole things, I simply want to kind of remind you here, this is our standard. And when we derive the standard, we know that the capital X divided by delta st and equal to 1 minus r squared plus 2 zeta r squared, right? So the blue one is our cheat sheet, right? So this black one is our calculated information. So here I just want to remind you how, once you have all the numbers, because here n, I0, R, CK1, whatever are given there, we plug in the numbers should be fine. And here you just pay a little bit more attention, and here I just want to show you how to plug in the right information into the right place. In these informations, we know we need R. We know R equal to omega n. So by all means, we need to calculate omega n, and that is k over n. And again, what is k? K is this value, right? And n is this value, right? So in terms of our system here, let me use black one. For our system here, so what is omega n? Again, omega n is the k term divided by m term square root. So what is the k term here? The k term is this one. So that is k1 plus k2 4 divided by what is the m term? This one, the whole thing. 4r squared. You good? Okay. So don't, because we're going to get used to using symbols, the common symbols to do something, to do symbolic calculations. But once to the final point, the final step, don't confuse yourself about the symbols you use. Okay. So here I just want to show you. And then we know the zeta. The zeta basically is equal to C over m and divided by 2 omega n. So again, this one, we've seen this one in fact half hour ago in our previous example here. So basically you can, for our case, how do you determine the zeta such that you can use in this formula, you simply plug in zeta equal to c terms. So let me write here. So zeta for our problem is equal to our c term divided by n term, and m plus IO 4r squared. Very bad. Okay. Can you read my notes? Okay, and then this divided by 2 omega n. So omega n has been calculated this one. So this is the zeta we've been calculated associated with these frequencies. Good? Okay. And then what is the, how to determine delta ST? So delta ST for our problem simply is the magnitude of the excitation F0 divided by K. And what is K? K is the two terms here, and that is K1 plus K2 divided by 4. Good? So once you have all the right informations ready, then you can begin to plug into our template, our equations for doing something. Okay, so that is the point of this example here. And yeah, so I think this one, by after plugging this one, then doing the number crunching should be fine. And we have 4 minutes. So let me proceed So for these questions, we want to determine this. We are given K1, K2, we are given C, M, and R, and I0. Here I use notation J0. And we are given F now, we're given the working frequencies. We want to determine the response, the steady state response. We want to get the steady state response. So basically for these questions, we're going to calculate the capital X. Okay, so easy. So we have all the numbers, you simply plug in, do this carefully. And so for that case, when omega equal to 20 radian per second, for this case, if you can exercise your calculation, capital X equal to 0.001136 meters. Okay, so basically we plug in all the informations, and you determine the omega n, you determine zeta, you determine delta ST. Once you have everything, then you determine R, that is 20 divided by omega n, you plug in here, that should be that number. Good? That is the one example. So probably Friday I would